Have you ever wondered how the maps on your phone find the exact fastest route? Or, how major cities prepare for massive storms literally before they even hit? Welcome to this explainer on the Bachelor of Engineering in Geoinformatics. It's this absolutely fascinating discipline where traditional geography meets cutting-edge computer science. We're going to explore together how this field is shaping the future of our planet and why it's becoming such a massive, dynamic career path.
Imagine for a second that you are sitting in the chair of an urban planning consultant. Your city is facing rapid population growth, plus the totally unpredictable threats for climate change. So how do you engineer the cities of tomorrow? Well, you can't just guess. You need precise, actionable spatial data. And that is exactly what a geoinformatics engineer provides. It's essentially the digital blueprint for the physical world.
Okay, let's dive right into this roadmap. We're going to systematically cover building resilient smart cities, the core syllabus and concepts, emerging versus traditional engineering, real-world applications and tools, career opportunities and salaries, and finally wrap up with overseas jobs and some final advice.
Section 1. Building Resilient Smart Cities. As an urban planning consultant advising city officials, you'd follow 3 absolutely crucial steps to drive sustainable development. Step 1 is data acquisition. You're pulling in oceans of information using laser scanning, that's LiDAR, and multispectral satellite imagery, which, honestly, is like giving you superpowers to see light across the electromagnetic spectrum that the human eye completely misses. Then, step 2 is spatial analysis and database management. You use geographic information systems, or GIS, to crunch all that data and pinpoint the exact vulnerabilities in a city's infrastructure. And finally, step 3 is visual mapping. This isn't just for us engineers, Creating connected, 3D visual maps massively boosts community transparency. It lets the public actually see and interact with proposed changes to their own neighborhoods.
Moving right along to Section 2, Core Syllabus and Concepts. Let's see how this all builds up.
To really grasp the academic rigor here, let's look at the College of Engineering Guindy at Anna University. This is a historic, highly prestigious institution in India. They only have an intake of 60 seats for this program, making it super exclusive, but with a highly accessible tuition fee of 48,000 rupees. The curriculum, it's the absolute gold standard. It perfectly blends physical earth sciences, heavy math, and really advanced computational techniques.
Now, what's really interesting here is the contrast between the intense theory and the empowering hands-on lab work. In your second year, sure, you're tackling deep math like probability and geodesy, which is the science of measuring the Earth's geometric shape. But at the exact same time, you're in the lab writing Python code and operating total stations. In year 3, as you get into microwave remote sensing and spatial analytics, you actually deploy to a mandatory 2-week survey camp to use these skills out in the real world. By year 4, you're literally designing decision support systems and tackling a massive capstone project, often working directly with corporate partners.
Next up, Section 3, Emerging versus Traditional Engineering. Let's look at how things are shifting.
And this brilliantly illustrates the massive shift in the professional landscape right now. Think about traditional branches like civil or mechanical engineering. They heavily rely on classical physics and physical infrastructure investment cycles. But geoinformatics, it's fundamentally data-driven. Because your core toolkit is packed with Python, SQL, spatial databases, and cloud computing, you are incredibly versatile. You're not boxed into construction. You can pivot into tech, defense, agriculture, or software development. And that flexibility really insulates you from localized economic slowdowns.
Let's get into Section 4, Real-World Applications and Tools. This right here is your professional toolkit. When you're briefing city officials, you're not just handing them dry spreadsheets. No way. You are showing them dynamic urban planning simulations that predict traffic and waste management needs years down the line. You're using digital elevation models, basically 3D terrain maps, to build flood inundation models, showing exactly which streets will be underwater during a major storm. You're analyzing satellite bands to track crop health for precision agriculture, and you're building real-time dashboards to guide evacuations during natural disasters. You literally turn raw numbers into life-saving strategies. It's a total game changer.
All right, Section 5, Career Opportunities and Salaries. Time to talk numbers.
In the Indian market alone, geoinformatics has exploded from a niche academic corner into a massively recruited corporate powerhouse. To put that into perspective, an average entry-level grad might start at around 7.5 lakhs a year. But look at the leap for an experienced GIS engineer. The average jumps to a massive 25.3 lakhs, with top pros pulling in well over 40 lakhs. Tech consultancies, infrastructure consortia, and software giants are literally fighting to recruit you.
And to prove just how incredible the local potential is, 36.5 lakhs. That is the highest placement package achieved by a graduating student from CEG Gwindi. It just goes to show that with the right mix of spatial analytics and software engineering chops, top-tier tech firms will pay an absolute premium for you straight out of college.
So, the crucial point is this. Your earning potential does not stop at the border. $137,000. That is the median global salary for a geospatial data scientist. These folks command top dollar because they blend advanced geosciences with intense big data research. The ceiling here is just astronomically high.
Finally, Section 6 oversees jobs and final advice. Let's talk global mobility.
The global GIS industry is on fire, projected to hit an 8.7% compound annual growth rate through 2034. And because there's a severe shortage of these highly skilled geospatial pros globally, incredible visa sponsorship pathways have opened up. Take Australia, for example. They offer the subclass 482 visa specifically for spatial professionals needed in regional councils. Across Europe, open data mandates and strict climate adaptation goals mean there's non-stop high demand for engineers fluent in ArcGIS, QGIS, and Python.
So, how do you capture these opportunities? Well, here's some direct advice from industry veterans. First, embrace AI. It's an ally to speed up your coding, not a replacement for your strategic geospatial brain. Second, build a strong portfolio right now using open source tools. You can even jump on Upwork or Fiverr to gain some early financial independence. And for a foundational textbook, grab a copy of Geoinformation, Remote Sensing by Gottfried Konechny. It's a classic that will absolutely anchor your studies.
I want to leave you with this powerful thought. This isn't just about drawing maps. It's about engineering solutions. You are the architect of resilience in a rapidly changing climate. Your code, your spatial analysis, and your databases will quite literally dictate how humanity adapts to the massive physical challenges of the next century.
So, are you ready to engineer the future and lead the way for tomorrow? If you're curious, if you love tech, and if you want a highly paid career that actually builds a better, more sustainable world, Geoinformatics engineering is waiting for you. Thanks for joining me on this explainer, and I hope this empowers you to take that next big step.